In this video, I will demonstrate the use of SAP and implementing the direct analysis method for a simple cantilever column. So we would start a new model, and when we click that icon, we have this new model dialog box, and you can choose from a set template, or you can create just a blank slate when you create your model. The new model initialization section provides us with information such as the default units of our model and the default materials that will be used for our model. So we'll keep it as kip feet for now, and the default material will be United States. So I'll select blank slate, and when you do that, SAP creates two windows to view the model. Two is not necessary, so I'll close one of them for now. Alright, and when you do that, the only thing you see obviously is just our blank slate and our coordinate system. So we will start by creating the geometry for this model. It will be a 12-foot long cantilever column. So SAP does not allow you to just put in input nodal coordinates. Instead of that, you have to create a coordinate system of grids. By default, it comes with the global coordinate system. There's no information in this, and it's just a name, global. So you can choose to fill out that information for the default system that was provided to you, or you can add a new system. I will be adding a new system just to demonstrate the process. So I'll put in Leo's grid. It will be a 3D grid system or coordinate system, and the origin is located at these global points. The orientation of our system will also be located at these typical locations. As far as rotation is concerned, there I will not rotate anything, so just to keep everything nice and orthogonal. Alright, you say OK. Here you can add the information for your grid data. X and Y and SAP are plan views, and then the Z direction represents the elevation, if you will, for all intents and purposes. So I can add an X coordinate by selecting add another one, and we'll put this X coordinate at, let's go at 5 feet. And even though I'm creating a cantilever column model, for some reason or another with SAP, you have to add several coordinate systems, at least two almost, in order to get them to appear on the screen. I'll demonstrate what that means in a second. So if I add in the Y coordinate system, we'll just call this A, and I'll add in B, and I'll add in a Z elevation, 0, add in another one, we'll just call it 12 feet, call this A1, A2. Let me delete this just so I could demonstrate. Well, I didn't put anything here, but I'll delete it anyway so that I could demonstrate what I mean by I need to add several grids in order so that it could appear correctly on the screen. So here I just have the X and I have the Y. Matter of fact, I'll just go ahead and delete this one just as well. Say OK. Say OK. and then we'll take a look at it in 3D, and we don't see anything. Okay, this is how SAP operates. So you have to be aware when you're putting in the coordinate system, it's not like just inputting nodal coordinates. All right, so it has to draw a line, I believe. So that's what it boils down to. So in order so it to draw this line, I can add another one, and like I said, I'll put it at 5 feet. Now I'll just do the X just to demonstrate, and I'll say OK, and we'll see what happens on the screen. All right. So here I can now start drawing my model if I want in that X direction. All right, so I have my grid. Now take a look at what it looks like in the XZ plane. Now in the XZ plane, you would expect to be able to see everything that is the other X coordinate that I've laid out, but I don't see that automatically. So only in the 3D view will I see this other grid line. Strange, but that's SAP 2000. Now, just to be consistent with my typical way of modeling structures, I'm going to go ahead and add my Y in this case because I want to use it just because it's a lot easier for what I need to do here. So I'll add another Y coordinate and I'll put it at 5 feet. Let's say OK. All right. Now, if I look at this thing in the X and Z axis, I see both lines. And if I look at it in the Y and Z axis, I also see both lines. So it matches what the 3D view shows. I'll go ahead and save my model. And I'm going to save this as my 3rd edition of this particular file. All right, so let's create the member. So here you can use the icons or you can use the drop-down menus. It's a typical graphical user interface that everyone is familiar with by now. We have floating toolbars that we can use. Pull it out, move it around, drop it to where we're comfortable with. You know, sometimes SAP shift things around once you start moving it. So you have to just be patient with the software because things will move. Let's just move this thing back up. I'll go ahead and move this away. Close it. I'll close it. And then put it back up in this location. Let's see where it goes by default. Just floats out. It's really annoying. At any rate, I'll drop it up here and see what happens. There we go. We'll leave it up there for now. All right, let's start drawing the model. I like to use the drop-down menus just as a demonstration of the way that you can access the toolbar in short and reliable ways without wasting time. So we'll go to draw. In this case, we'll be drawing a frame element. So we'll select that option. Now, the properties of this object has been set by default. These are all default properties that come with SAP, and we will modify them in a later portion of this video. So just draw an element from my 0, 0 to 12. Save. Now I don't see my nodes. Right? The reason why is because you have to display them. There are display option settings. So we'll come over here and I will show my node in terms of actually just making them appear by deselecting the invisible option under the joints box. If I want to see the numbering, I'll go ahead and select the labels for those nodes. I will go ahead and turn on my section so I can see what type of section has been applied to this frame element. I am going to select restraints. Once I apply restraints, this will be active, and I can see that. The other tab will give us the different view types that we can look at, and other things related to the analysis model itself. All right, so we'll get into that as we do the work. I'll say OK here. Now the way that SAP works is that once you've created these objects, in order to apply a property to it, you have to select it first, and then you can assign it its property. So I will assign here, I will assign a fixed support. So I select the node, and then I go to assign joint restraints. Okay, these are our typical reactions, global reactions that we could set for whatever support that we want. Okay, these fast restraints are fixed, pin, roller, or free. All right, just selecting one, you would see that you can get those restraints easily, or you can customize it based on whatever that connection looks like. In this case, it's a fixed connection at the base, so we select everything. Hit apply, and there you have it. It shows up with the base. So come back over here, and you can see my restraints options. It's now active, and I want to make sure that I keep it on so that I can see it. Let's do something real quick to clean this up a little bit. Now that I have my model set, I don't really need the grids. It's just kind of cluttering up the scene. So I'll turn it off. Say OK. You can do the same thing by turning off the axis if you want, but I like to keep my axis on just because it gives me a great feel for my orientation. Must stay oriented. All right, now the next thing to do is to assign some material properties and section properties to our frame element, the proper ones that we want to use. So here I will be defining a W 14 by 30 section. So I went to my define section properties, frame sections, and here by default, like I said, SAP out of the box comes with this property. I can import a new property. So import. So here the drop down box will give us material options for what we want to import. Here I'll be importing a steel property, a typical I-beam / wide flange. All right, bring this guy in. And right here, you can see the material is already set at 8992 and 50 KSI. It's the default material that's in the box, that's in the database. I will modify that at a later point if necessary. In this case, it's not really necessary, but I'll demonstrate the process. So if I'm going to bring in wide flanges, these days all wide flanges are pretty much 50 KSI and 8992. So I'll just go ahead and bring in this case, I'll bring in all of them just because it's a lot easier when I want to change the properties in the future. I say OK. All right. Say OK to that. Now, I will now assign that property by selecting the member and then going to frame sections. And I get my assign frame section dialog box. Search for what I want. I could scroll through, or I could go to define sections and just kind of look for what I want. It has like a search feature, so that automatically gives me quick access to my elements. Hit apply. You would see that the search, or it should be there. Okay, it didn't take. So in this case, it requires you to search for it. Again, I have to select my element. And then hit apply. Alright, say OK. Let me pause this for a second. Okay, now that we have the element defined, we'll just go ahead and take a look at the definition of some material properties. So here, typical way that you would do that is go to define and material. And if I wanted to import another type of steel, for example, let's say I wanted to import A36 steel. Go to add. From the drop down menu, you can either add A36 if it's already selected. If it's already available, and then say OK, and that imports it. Excuse me. Say OK. Of course, you can assign that material pretty much in the same way that you did with the frame section. I come over here to material property overrides, and I can overwrite whatever material that's already in there by making that selection. So here I'll keep it as 50 KSI. Now I'm overwriting it. It doesn't make a difference. So okay, let's take a quick look at this thing in this 3D view by taking a look at our display options. Come over here under view type, select extrude, hit apply, and now we can see the three-dimensional view of our element. You can rotate it by holding down the mouse, the middle mouse button oftentimes with the shift key, and rotate it. Zap is kind of weird where this thing kind of disappears a little bit, so it's a bit annoying, but if you work with it for a little bit, you get the hang of it. So anyway, we'll keep it in 3D view. Reason why we want to see the 3D view is because I want to have this cantilever column bending about its weak axis. In this case, its weak axis, as far as moment of inertia is concerned, is, would be when I basically bend it, by putting a force in the y direction. So I like to say the weak axis is oriented towards the y direction in this case, and the strong axis is oriented towards the global x direction, the global y direction. All right. There's a way to look at it locally. SAP doesn't call it X, Y, and Z. Instead, they call it 1, 2, and 3. We'll take a quick look at that. Go ahead and put this in our 3D view. Come here, and you have to turn off your, as far as I know, we have to turn off the extrude in order to see it. And then we'll turn on local axis, hit apply, and you will see our local axis X, Y, and Z. So the way that I remember what's X, Y, and Z, or 1, 2, and 3, is the colors that SAP has. It has red, green, and blue. As red is 1, green is 2, and blue is 3. So red is 1, which is X. Green is blue. Green is 2, which is Y, and blue is 3, which is X, as far as X, Y, and Z coordinates are concerned. All right, so always just keep that in mind. It's not color coordinated. It's not coordinated with the global axis. So you have to pay attention. So red, green, and blue. I think about it like red, white, and blue. We talk about the US, and that's how I tend to remember it. But instead of having white, it's green. So red, green, and blue, not red, white, and blue. That's kind of my method of remembering it. Let's see if it could actually show you your labels. I don't think it could show it doesn't. So you have to go into the help to take a look at it. It doesn't actually label it. These are some what I consider to be odd features of SAP. All right, structural engineer must pay attention to this information. Go ahead and turn it off. Like I said, I'll keep it in. Oh, by the way, I believe if you go ahead and put it on extrude and you do the same thing, you don't see our local axis under the extruded view. So extruded view turns off our local axis, and going back to standard would show it. All right, I like to keep it in extruded because it's just easier to work in 3D. And I'll go ahead and turn off my local axis for now. So now that I have the structure defined, I have my cantilever column that's defined. It has the proper sections. I could double check that by selecting it with a crossing window that turns into dots, or a crossing window the other way. It also turns into dots, and you select it. Now you can right click. You have to right click on the line. That brings up the object model information. In this case, you can see that it's a line object, and here it would list the various properties that has been assigned to it. Provide some geometric information here. Any loads that has been assigned directly to this line object will be shown here. Any design overrides that's applicable will be provided under that tab. All right. The one thing I want to pay attention to right now is that there are no property modifiers being set right now. Okay. The direct analysis method requires us to modify the stiffness properties of our frame element, and we would modify our axial stiffness as well as our bending stiffness, EI. And we could do this manually here if we want, or we can do it in the automatic set state. I want you to note that if you do one, you cannot do the other in the automatic state. And I'll show you what that means in a little bit in this video. But just pay attention that I have not modified anything here at all. All right, I want the software to do it automatically. So this is important for the direct analysis. I'll say OK. All right, material overrides that was provided, any releases, so forth and so on. You could go down the list and figure out, what you need to set. So we'll say OK to the screen. Now, when I define my loads, SAP define loads, this basic load, what we would be calling like a load case, as is listed in IBC or AISC 7 as a typical load case. SAP doesn't call it load case, they call it load patterns for whatever reason. By default, it has a load pattern of a dead load that's in it with a self-weight multiplier. So this is our self-weight load case. And I like to modify this thing to say self-weight so that I could better identify that load case. Note the self-weight multiplier. I'm going to add another load or other loads, and I can do that by selecting the load type that I want. If it was a live load, an earthquake load, a roof load, snow load, wind load, etc., I would make that selection. This is important when you're doing a lot of automation. Here I'm going to be doing everything manually, so I want to go ahead and put it in as other. All right, Don't necessarily have to do this. I just like to do this in order so that I'm consistent with my own methodology. So I'll put in other. Um, Note now the self-weight multiplier must be 0. If it's 1 or any other value, right, you will be multiplying that factor by whatever is the weight of the member. If I put in 1 and I put this load into the structure, I'll be doubling up on self-weight. All right, so that'll be a problem. So I'll call this my vertical load, vert, and add this new load pattern. I'll go ahead and add in one for horizontal. So now I have load patterns to represent my vertical and horizontal loads. Really basic. Also have the self-weight included in the analysis. So say OK. Now the reason why SAP uses the term load pattern, in my opinion, instead of load cases, is because it actually analyzes its load cases. So these load cases will be analysis cases, if you will. So we'll come over here and take a look at what I'm talking about. Now, there are the defaults that were there added, the dead load case and the modal load case, and the other two that I just added. All right. The load case type will be the type of analysis that will be applied to it. A linear static analysis is a first order elastic analysis, which does not take into consideration things like geometric stiffness or material stiffness issues that are related to the behavior of the stiffness of the structure. All right, so this is a typical stuff that we learn, basically what I like to call as structures 101. You know, that everything that we're analyzing is pretty much in the elastic range under structures 101. That's what you have when you look at your analysis results from your basic statics books or mechanics of materials books. Is presuming a linear elastic analysis for the most part. Okay, so here again you can see that the load case is named dead. Even though I modified it to self-weight, it didn't change it because this is the default of a load case. It's actually, it was created as a dead load case automatically by SAP. Here I'm going to modify that. I want dead, like I said, to represent self-weight. You see, so it's showing self-weight down here, and I wanted to match it as a name. Self-weight. Again, we'll keep it as a linear analysis. Say OK. Modal. This is to determine our natural frequencies of our structure, and I'll get into a natural whole modal analysis video at another time, but this is related to our natural frequency, so we could determine the period of the structure. You know, when we want to do more sophisticated earthquake analysis, we will use that. It's also good when you want to investigate the stability of a structure. But here I'm going to investigate the stability of the structure using the direct analysis method, so I'm not going to use this feature right now. All right, so we'll delete it just so that we don't have to clutter up our database with unnecessary information. Now, I have a vertical load case and horizontal load case. Just take a quick look at it, and you know, like I said, straight linear elastic analysis, and that's fine. And this would just be, like I said, analyzing that particular load case. Here, whenever we do the direct analysis method, we have to analyze both the horizontals and the vertical loads together at the same time. Linear elastic analysis does not do that. It does a superposition of the individual load cases analyzed one at a time. So here we're going to create a new load case in which we combine our dead and our live and analyze it together linearly, non-linear in this case, and not use superposition. So I'll add a new load case, and I'll call this 1.6 V plus H. Now I'll explain this 1.6 factor in a second. It's basically related to the fact that we're using I'm planning to use the allowable strength design method for this particular example. And in AISC, you will find that when you use the direct analysis method and you design a structure using the allowable strength design method, you have to use a 1.6 factor during your analysis in order so that you could analyze the loads at the strength level. So here we'll add our 1.6 factor and we'll add this load. We'll go ahead and do the same thing for our vertical. We'll add this load. Do the same thing for self weight, and we'll add that load pattern. Now, as I was saying before, our analysis type must be nonlinear. So we'll switch it to a nonlinear, and we will use our geometric nonlinear parameters. If we have none, self-explanatory, it doesn't apply. I could use P delta or P delta plus large displacements. You can go into the SAP help in order to determine the difference between the two, but understand for now, all that's needed for us is the P delta analysis. Again, this is what I would typically be doing. Excuse me. We could go into help and find out more about this, but this P delta analysis is what's needed for our purposes using the direct analysis method. We'll say OK, and that gives us our load case, and we say OK to that screen. Save the file. And the other setting here would be to come over to our design and go to a steel frame design section and set our preferences. This is the location where we tell SAP that we're using a particular code and we want to analyze using a particular method. So here I will be using my AISC 360 10. I could use 16, but I just want to use 10 for this example because most people will have 10 and not 16 as far as local building codes are concerned. Frame type, I could leave it as a special moment frame, or I could modify it as I desire. I like to use an ordinary moment frame because I want to avoid any potential default settings within SAP that might apply to a special moment frame or intermediate moment frame. And this is all related to seismic design, so that's something you will pay attention to if you were implementing seismic design. My seismic design category, I'm just going to leave it as A, actually. I basically don't want the seismic to come into play for what I'm doing right now. Excuse me. I want it to be only a straight analysis of dead loads and vertical and horizontal loads. At any rate, I like to just go ahead and set the factors that I think might affect me. So I'll change our redundancy to 3. I'll change our overstrength factor omega to 3. I will change our deflection application factor to 3. Again, this is related to seismic and just what I like to do in order so that I can make sure that I nullify SAP 2000 as far as implementing anything related to seismic. Here's where it's important. Our design method will be the allowable strength design method. Our analysis method will be direct analysis. This is important. Now, we could use our effective length method in order to design for stability, or we could use a limited first order analysis based on the criterion that is found in Chapter C of the AISC 36010 manual. Alright, so we're using direct analysis, and we're going to use a second order method, a general second order method, and not use um, amplified moments. This is the old school way. Amplified first order and basically effective length would be the old school way. Alright, that's another video, and I'm not using that. So we want to use direct analysis, and the reason why we want to do all this is because we want to keep our K value as 1.0 in order to eliminate any problems in determining K. So this is a little bit more generic. It's also known as a poor man's second order inelastic analysis. That is, the direct analysis is essentially a modified second order inelastic analysis. Okay. The second order elastic analysis well, actually it's going to be elastic, not inelastic, but we're using elasticity here. All right. For those that are structural engineers, you would understand exactly what I'm talking about. And if you need to do some research, you can hit me up in the chat and we can talk about it a little bit more. Alright, so our tau sub b factor, we're going to change it to variable here just to see if that's going to modify, if we're going to need to modify our stiffness again at another point in time. So this will tell us whether or not that's applicable. So here we're going to leave it as variable. Other settings here are pretty much the standard settings with the allowable strength design method. This omega factor, actually our factors of safety for bending, compression, tension yielding, etc., etc. One thing to pay attention to is our demand capacity ratio limit. The setting for that here by default is haphazard as 0.95, which essentially means that you will be taking your structure to its limit of 95% of being utilized. I like to go a little further than that, 99%, not 95%. Reason why I do that is because I know my structure already has factors of safety built into it as far as the capacity, and the code allows me to do it. In fact, I could go to 1 by legal definition, but no structural engineer in their right mind like to do that. We like to be a little bit more on the conservative side. Here I'll just take it essentially to 1, but I'll stop it at 99%. We'll tab out of that, say OK. Now, reason why this is important, again, let's just go back real quick. This is important to set this because this is where your property modifiers will come in. Alright, with this setting, with this direct analysis method setting, under the analysis method, the structure will be internally modified during the analysis. Alright, so that's how SAP take care of our modifier. You're going to actually need to run the design twice in order to run the analysis twice in order to do that, and I'll show you what I mean. We'll say OK to this. Now let's take a look at our loads, as we don't see anything here. We want to make sure that it's loaded. We could do this by 2 ways. One way is to display the load on our objects, in this case the joint load. Unfortunately, you can't display the load cases at the same time. You can only do the load patterns. So here I could say if I had any load in there, it would show, but say I didn't put any loads, and therefore this is not active. So this is a way for me to go ahead and verify whether or not I put any load. So I know no loads are on this structure right now, and I could also select the element and right click, and I don't have any loads shown here. So apply some loads. For my vertical direction, I will apply a load of 32.7 kips in the vertical direction, going down. Why 32.7 is because I've actually calibrated the structure to fail at that load. Went through various analysis to determine that, and 32.7 is what I'm going to use. So I select the node and then I say assign here, not the joint restraints. That's not applicable. You have to go to joint loads. Okay, and I will assign a load in the vertical direction. I tend to always use our global system. Okay, I can use Leo's grid. Doesn't really make a difference because our two systems are together. But if you use local, it's going to make a difference because it's talking about the member orientation. So here I'll use Leo's grid. And say minus 32.7 and hit apply, and the load appears on the screen. Switch over and add a load horizontally, and I will add what is L over 500 for our lateral load. And again, this is part of the direct analysis method. So what that does, that L over 500 is taking into consideration that when you erect a structure, things are not perfectly straight, even though our drawings show everything straight and perfectly aligned. That is just an illusion, because when we erect a structure in real life, the structure will not be perfectly aligned. In fact, it will not be perfectly straight just as well. It will be within a certain tolerance that is associated with our code of standard practice. So in this case, our out of alignment tolerance is L over 500. All right, L being the length of the member or the story in this case. All right, we're allowed to have a deviation laterally of L over 500. L is 12 here, 12 feet, and that for our situation, that's going to give us a value of out of plumbness of 0.288 inches. Now I can model that out of plumbness, or I could put in a load that would have the same effect of having it out of plumb. Here my structure is modeled straight, so I need to put in that load. All right, so that's a long explanation of why I'm going to use this particular value, but it's basically taking 1 over 500 and multiplying it by your vertical load. In my case is 32.7, and that gives me a value of 0.0654 kips. Okay, now I'm putting it in the Y direction because, as I said earlier, I want to bend my structure about the Y direction, and I'll put it in the positive Y direction. All right, just because that's the way I like to do things. It could be negative, doesn't make a difference. You'll see your structure bending in the opposite direction. Now, one thing to pay attention to also is that you want to choose the option that applies here as far as adding to an existing load or replacing an existing load. If you were to somehow have loads previously defined, and you chose replace, it would change it. It would replace those loads. So make sure that you use add. I like to use add, just so that I know everything is being installed and I'm not overriding anything. So we use what's applicable. We say okay. Oh, it didn't take. Why? Because I didn't select the element first. So go back here and make sure my node is actually selected, and I can apply it now, and you'll see our load appear. Save the file. So now I have everything. I have the structure defined, I have the supports, I have the material properties, I have the settings defined, I have the loads applied. I'm ready to go. Alright, one thing I didn't do yet was actually modify any type of automatic meshing. And that's because I want to demonstrate to you the effects of automatic meshing in SAP. So you know what I'm talking about. I could select the element, and I come over here, and under my frame properties, I have the selection for automatic mesh. Okay, this determines how my member is broken up, if you will, during analysis, how it's put into parts during analysis, and that affects internal nodes, that affects the actual results that you're going to receive. So it's important to understand that this automatic frame mesh setting will affect your analysis. So as a structural engineer, you need to pay attention to it. Here, the parameters is set at only as intermediate joints. So I could break it up if I wanted to, but like I said, I will demonstrate that in a second. So we'll say okay. Now we're ready to rock and roll. All right. Let's go ahead and run this analysis. And oh, by the way, to make sure that I'm doing a 3D analysis, I could have the set analysis options dialog box show up, and 3D space frame. If I want to do a 2D, do that. I could select whatever I want. Plane, space, truss. Truss, by the way, it won't take into effect any type of rotations. It'll just be axial, and no frame action, no bending moments in theory. All right, but anyway, we'll run the frame because this is the whole kit and caboodle. All right, so okay, there are other options here related to the solving, the particular solver that SAP would use here. We don't have to modify anything here. We'll say okay. Come over here and we can set our cases to run. So what are we going to take a look at? We're going to have these 4 load cases analyzed. One of the 4 is a nonlinear static analysis. All right, this is where it's important for us. We'll go into load combinations after this. I know I haven't set my load combinations yet, but we're just running the analysis. So there it is. The analysis ran. Took a little longer than I wanted to, but anyway. And it automatically, SAP automatically shows a deflected shape. You know, in this case, the self weight. Our units can be modified here on the bottom. When I say modified, I mean changed in terms of the setting. So you can change from kip feet to kip inches. Anytime you look at displacement, you probably want to look at inches instead of feet, right? So on the self weight, I get this value just by hovering over the node. If I want to look at what do I have for my displacement, and let's say I want to look at the effects of the linear static analysis. Again, first order elastic analysis, by hand, we could come up with the same number for a cantilever column. Take a look at what that displacement is, and you can see just a linear static analysis would give us a very small displacement. All right, in this case, we have 0.115 inches. All right, that's the lateral deflection. Let's take a look at this in the XZ plane so you could kind of get a better feel for what I'm talking about. All right, this thing decides to disappear on me. Zoom into it a little bit. There we go. Again. Now, if I look at what is the lateral deflection under our load combination of 1.6, this value is actually going to be large, very large. and it's going to be incorrect as far as if you were to think about this as your sway. All right, and I'll explain that to you in a second. So here we'll see a large value. Oh, I forgot. It's actually not going to be so large right now. And the reason why it's not going to be so large is because our property modifiers haven't actually been applied to the structure. Now this goes back to earlier discussion. So here we'll see under 1.6, and we have a larger deflection than what we had just looking at the horizontal load alone. Again, didn't take P delta into effect. No nonlinear effects are applicable here. But as far as the horizontal load was concerned, anyway, we have a deflection that takes the P delta effect into account in this case, just geometrically. All right, so now we have a deflection of about 3/4 of an inch in the lateral direction versus what was about 1/8 of an inch the first time. All right, we might even think that if you didn't know, an inexperienced engineer would say, oh, I have a very small deflection, and this thing is actually multiplied by the 1.6 factor. Okay, that would be completely incorrect. All right, so this is where, it pays to understand what you're doing. And if you are subscribing to my channel, my goal is to make sure that you understand what you're doing as a structural engineer. And that way we don't have large mistakes that will come to haunt you and your company, and perhaps the lives of other people in the future. So subscribe to my channel and you will learn more about structural engineering, all right, and what mistakes not to make. Anyway, that's my little speech. So take a look at this thing in 3D, and again, go ahead and right click on this. I want to see whether or not any type of modifiers were applied. Here, no modifiers were applied. All right, we need that in the direct analysis method. How do I apply the modifiers? Well, actually need to run the design here. Now I could do that by just going over here to my select design combo. Here you can see I don't have any combinations available. Why? Because I actually did not create any combinations to begin with. And I could have done that during modeling, before I ran the analysis, or I could do it afterwards. So here I'll define some load combinations. Again, I'm going to do this manually. You can add some default design combinations. You could even convert those combinations to nonlinear cases for analysis. Again, this would be a before analysis option. Here I will just go ahead and demonstrate how to use the manual process. So I'll go ahead and bring in a load combination. I'm going to make this load combination 1.6 times AISC. This is just a name. It doesn't mean anything analytically. This is just a name in this case, right? The actual analytical implementation of this equation will be done through scale factors. So here now I want to take my load case that was factored by 1.6 and divide it out by 1.6. 1 divided by 1.6 is 0.625. Why I am doing that is because we're using the allowable strength design method, and in SAP 2000, unlike some other programs, you literally have to do this yourself. So it's a manual implementation that's required by the engineer in SAP 2000. There is no, as far as I know, there is no automatic way of doing this. If you know of something, leave a comment in the comment section below, and we'll discuss it. But in my years of experience and talking to SAP and their technical support, this stuff has to be done manually. You could also, I believe you can find this information in the help of SAP 2000. Anyway, so we bring this thing in. Now this will be my load combination that I will end up using for design in this case. All of my load combinations, if I had 100 of them and they were all AISD and they were combining my vertical and load combinations, I would need to do that for each one of them. Alright, now that's very annoying, but that's SAP 2000. So we'll go ahead and say OK to the screen. The other settings are fine just the way they are. Nothing else need to be modified. Say OK. Say OK. Now again, going back to design, come over here and you would select design. Now my load combination is here. I'll go ahead and put it as a design load combination and say OK. Then I'll click this button. You can just click the button and we'll start the design. Alright. So here you might think I've designed this column and I'm good to go. Well, that would be wrong, because again, like I said before, you actually haven't implemented the direct analysis in its full requirements at this point. So I could go ahead and take a look at my interaction ratio, and here it would show me what's the stress ratio. Here it's a measly 0.36%. An inexperienced engineer might think they're good to go and walk away. This could be done, like this type of mistake might happen for an entire structure, entire building sometimes. I've seen it in some design offices where young engineers or arrogant engineers or older engineers that just don't know how to use the software, they would walk away thinking the structure is designed. It's wrong. It's not designed here. How do I know that? Right? So now I could select my element, right click on it under this scenario, and I can find out more information. Alright, and what I mean by that is right click, I can actually go into the details of the design and find out more information here about this thing. Now because I've ran my design, go ahead and unlock the analysis. I've actually applied modifiers automatically. That's the process of applying these property modifiers. Now that the structure has been modified, I actually need to go ahead and run the analysis again. Okay. Remember, the deflection was 3/4 of an inch under the 1.6 load, the load case. I want you to see what it is now. Alright, right click it. Now I have a deflection of about 7 inches. Okay, from 3/4 to 7 inches. Why? Because we've modified the stiffness. This is taking into account material nonlinearity. Again, you're going to learn that this might get us close, or it might not get us close to enough of where we need to be. But this is pretty close in this case to our final solution. Let's go ahead and take a look at the XY plane. Now I'll go ahead and run a design on this. And the structure that was working before is failing now. Okay. Check out the stress ratio, and it's exactly at essentially 1.005. So you could take a look at our moments, our design moment at the base here. We didn't do it in the previous version, the previous run, but you could check it out on your own. But you can see what our design moments are here. You can show the values instead of filling the diagram. That'll give you information. In this case, we have a moment of about 230 kip inches. Okay. And essentially, you might think, okay, now I'm good to go, 100%. In this case, I calibrated the structure to fail at that load. You know, I want to demonstrate the effects of making modifications to the mesh. So I'll unlock this, and we'll see the effects of making modification to the mesh setting. I'll do that by copying this thing over. Okay. Let me change the view for a quick second while I do that. Put it back in our standard view. And I'm going to replicate this member over. I'm in inches, so I'll go ahead and move each one 5 feet apart, replicate it by 3, add 3 more in the Y direction. Oops, I didn't select everything, so meaning the nodes and the elements, so I didn't get a copy of my supports. And by the way, I didn't get a copy of my loads, so I could click right here, and I could see my loads weren't copied over either. All right, this is again something that can cause an error if you're not modeling correctly. All right. Of course, you would just have to go back and input those loads manually, and you will see what happened when you run the analysis. You'll see the effects of that. Anyway, delete that. Let's just copy everything all at once by selecting the model. Everything in this case, and doing the same thing. All right, now my loads are copied over just as well. Right click on it, take a look. You can see I have my loads as well as my reactions. Save it. Now I am going to show the analysis model for this thing real quick. All right, this is what the computer sees when it runs the analysis on the structure. Add apply, and you will see. Now my computer sees basically just one line element with 2 joints. That's based on my automatic frame meshing settings. I'm going to take this and add an intermediate load, right, internally, without breaking the member up, right, into different pieces. If you break the member up into different pieces, that will also affect your analysis. You have to take a look at some other videos in order to view that, but that would affect the analysis because the computer would just basically think the member is going from node to node. That's a manual division of the elements. Here I want a kind of internal division of my elements. So this is the best way to do it. Come over here, take minimum, I'll make this 2. Now you see the word yes appears, which just means that some type of frame mesh has been added. It doesn't show you what's been added. And if you want to see it, you go and you say show the analysis model. Alright, so now we see 1. I will show the sections here so you can see that internally it thinks it's 2 elements. Okay. When I select it though, I get the entire line. Right. I'm going to do this right here, and I will add 4 to this. So we'll just keep multiplying it by 2, keep doubling up on it, and see the effects of that on the design results. So 4. Come over here, we'll make this one 8. Hit apply. Alright, we're almost to the finish line. I'm going to say OK. Again, I'll show you what it looks like as far as an analysis model is concerned. So now we have this thing all set and ready to go. We'll take a look at the effects of breaking it up into more parts. Run the analysis. And by the way, not all programs allow you to do this. There are also some error checking methods that can be used. We can go over that in another video, but some programs will not allow you to break up your model like this because it's not designed for models that are not connected. So disjointed models are not allowed in some other programs, or they'll give you errors or warnings and you have to pay attention to it. Anyway, we could take a look at the effects of this by coming over here. Oh, it's already set. So you can see our different moment values. Slightly different moment values are obtained at the base. With just one element, we have 230 kip inches. Two elements are giving me 267 for all intents and purposes, so 266.9. Three elements is giving me 268, and four elements actually is kind of going back to 268. Went down. Interesting. At any rate, we can see that the 4-element model and the 8-element model essentially converged on the same solution. I'll demonstrate that by running the analysis, running the design, and showing our stress ratios. Okay, so we went from 1 to 1.13, if you will. And you can even say at 2 elements they converge. So 2 elements would be the absolute minimum. 4 elements would probably be, more than enough. But it would be what a conservative engineer, depending on the sensitivity of the structure, probably would want to accept. Having more than that doesn't really affect your anything other than analysis time, but you can get a little bit more detailed information. So that is the difference. I will actually go ahead and show you something that does work, since this section is not working at that load and these values. I will just go ahead and copy this thing once more. Again, I could take a look at our member properties, show undeformed shape here, and in fact I will not show my analysis model anymore. Right click on this one, you can see my EI properties have been applied. So okay, cancel. Come over here. This has been applied, and so forth and so on with the other ones. So it's important to break your elements up at least into 2 parts, even when you have a geometric nonlinear parameter being defined, because you're actually going to get more bending. Having that intermediate node will give you a more accurate analysis. All right. Now let's just go ahead and copy this over and show something that works. So I'll take this column at 14 by 30, and I'm going to copy over 2 elements. Create 2 more elements here. Why 2? Because I could take this column and bring it to its next size, right? Which would be a cancel. Let's see, what do we have? Under the 14 by 30s. Under the 14s. The next section up, I have my book open in front of me. In fact, I should get it real quick. But looks like the next weight up is the 34. Let's open this thing up real quick. Alright, yep, it's the 34. I'll select that. Say OK. So that might be a way of saying, oh, let's go to something that I know will work, and the lightest section that I could use is the next section up, the 34. I like to use kind of square columns whenever I design a column. So our typical column section that you would want to start off with, it's a little insider engineering, structural engineering knowledge, would be the one that is boxed, is more square, i.e. the flange width is kind of equal to the depth of the column. For the 14 sections, the W14s, that starts at the 14 by 43. You'll see going up from there that the rest of the sections are pretty much boxed, or it start to get to a situation where the flange is actually outgrowing the depth. Okay, so here I would say, like I said, I'm going to go ahead and apply the next section. There was two ways to doing it, but I'll just do it the traditional way. Wrong section. Go here. Frame section. Go up to the next 14. Apply. Now, if I want to use the right column, like I said, it's better for detailing purposes and just making life simple, having a box section in this case. I would use a 14 by 43. That is a better section to use for this particular column. Come over here. And this is it. I'm going to bring it home by using this 43. Apply. Again, I know I have my segments broken up. Double click on this. Actually, let's see, right click on this. This is broken up into 8 segments. We know it's going to be absolutely correct and everything we need. So it doesn't get any more correct than this. Alright, this is the final solution. I could leave it as 4, but I chose 8. Whatever. So run the analysis. There we go. You can see bending has dramatically been reduced. And why bending has been reduced for these other 2 columns is because the deflections are reduced for these other 2 columns. These other 2 columns are a lot more stable. We could take a look at that under the 1.6 AISD divided by 1.6 factor. This would be more realistic as to what the deflection would be under this analysis. You can see what was previously, it was like 7 under the 1.6 load, but these are the real ones. These are the real deflections. So we have 5 inches, and this one right here is less than an inch. It's almost 3/4 of an inch. Still probably not something that I'll be comfortable with at 3/4 of an inch, but it's tolerable. Alright, let's check my section that I would use for design. It's 1/8 of an inch. This is what separates the good engineers from the great engineers. Alright, so knowing that you want to use something a little bit more stiffer, you don't want your structure moving that much. In fact, you probably don't want it moving at all. But this is within reason. Alright, 1/8 of an inch in this case for our W14 by 53. Go ahead and run the design again, and we'll see what our stress ratios are. Here we go. So this one right here is about 33% stress. This one right here is not even 10% stress. this is the best design, in my opinion. Alright, and that's it. This is the implementation, or this has been the implementation of the direct analysis method using SAP 2000 for a simple cantilever column. Subscribe.